Hi, this is a high performance in Java, Java 9 performance and compiler enhancements, and this is the third section. And in this section we will be looking how compilers help us to achieve best possible performance. This is a very important topic because in Java 9 we have a couple very important compiler improvements. But to understand those improvements, firstly we need to understand how compilers really works and how compiler helps Java code to be more performant. So it is very important matter to know that. So in this section we'll be looking at the just-in-time compilation. This is the most important thing that is in the Java in JVM, and we need to understand it properly to look at other subjects. Second subject will be ahead of time compilation that will be introduced into Java 9 and segmented code cache. At the end of this section we'll be looking at the summary of Java 9 performance improvements. So this is the first video, and in this video we'll be looking at the just-in-time compilation. So we'll be looking at the Java bytecode. That Java bytecode is interpreted when program is starting, so it is very slow. And just-in-time compiler is finding a hotspots and compile them into machine code, into assembly instructions that could be executed by the CPU directly. We'll be looking what are the hotspots and what are the common JIT optimization that can affect and always affects our code, and how to leverage them when we are writing our code. So let's look at the first question, what that bytecode is. So firstly, when we are creating a Java code, Java class, this is our Java file. When we want to start our program, we need to start Java C compiler directly or indirectly, like from the IntelliJ or other IDE. After it is compiled, it creates a bytecode class. So this all files with the .class extension. Those are the bytecode instructions, and that bytecode is interpreted. Bytecode is needed because when we have multiple JVMs that run on top of the different environments, different operating systems, like in this first example, JVM on Windows, in second JVM on Linux, JVM on Mac. So that bytecode is common for all JVMs. So this is like interoperability format. So this is like Java slogan, write once, run everywhere. Thanks to that bytecode we can achieve it. So each JVM will start that class and execute it independently from operating system. So our java code.java file can be executed on any OS. What the JIT is really. So as we see on that example, when we have the Java source code compiled into Java bytecode, that class files, it is loaded into JVM, Java Virtual Machine, and then that code is interpreted. Java interpreter is interpreting line by line and executing it. And as our program is running, everything is interpreted from the beginning. Then after some time, when JIT, Java just-in-time compiler, finds some places in code that could be optimized, that hotspots, it can perform compilation of a small portion of code. So the small portion of code that previously was a bytecode, right now is compiled and injected into the resulting code. So up to this point, when our execution path is on the code that is frequently executed and compiled by JIT, that instruction is no longer interpreted, but those are an assembly instructions that will run in the native machine code against operating system, and this will be a lot faster than interpreting it. But disadvantages of it, because that code that is compiled is not portable. So once that will be compiled by the JIT, it can only be executed against that particular special operating system. So if our program is running against Linux, then our JIT will compile bytecode into the Linux native machine code, native assembly code, and that will be executed against that Linux kernel, Linux operating system. So therefore, firstly we have interpreter that interprets bytecode, that is interoperability between Linux, Windows and other operating systems, so it's portable, and JIT is compiling it to the assembly instructions that are not portable, but faster. And what the hotspot is. So this is a part of the code that is executed many times, and therefore its performance matters a lot to the overall application performance. So when we have where we have some code paths that are executed very frequently, JIT can measure it and compile it. So JVM is measuring where the most part of program takes place and compiles those hotspots into assembly instructions. And assembly instructions are not portable, are generated especially for particular operating system. So let's look at the common JIT optimization. This is a very fun and interesting to see how does it behave, because it affects our everyday code. And first, JIT optimization that is really easy, let's say, for the program, for us it's not so easy, is null-check elimination. So let's say that we have a ransom algorithm method that takes an argument graph, and that graph could be null. So programmer, when writes that code, needs to check against that null. So this is a defensive coding good practice. So it checks if graph is null, then return or do something else, and if not, then actual logic is performed. But when that code is interpreted by the JVM, it has some measurements. So it can have a counter of how many times that graph was null, so that if was entered, and how many times not. And if there is some threshold, that is some, let's say, threshold of 1000 of invocations, and if 1000 invocations graph was not null, then compiler will optimize it, and that becomes this. So it removes that null check. So then when that path is executed again, it is a lot quicker because compiler optimized it in this way. But it also needs to have some save points, because sometimes that graph could be really null. Then in that point it need to jump back to that bytecode interpreted code, and again the measurement will take place again, and if counter will be above some threshold, it will be compiled again. Second very important optimization is branch prediction. So let's say we have that example that we have an method that takes two arguments, x and y, and it performs some logic. If x is greater than or equal to y, it does some calculation in one way, and if everything else, it does some calculation in different way. And also it is measured, so it has counters, how many times is if, how many times is else. And let's say that in every case y is less than x, and JVM sees that every time that code is executed, it goes into the else block. But still it needs to check that if, because this is a first condition, so it takes some time. It needs to check if x is greater or equal to y. It is not true, so it goes into else block. But when the JIT see that, it could compile it and optimize it in this way. So it switch the if and else conditions, and right now if became that first condition. So if x is less than y, then execute some logic as that first block that was here is greater than y. And due to that fact, when y is less than x in the all cases, that code will be executed faster because it doesn't need to check that first condition. First condition is always true, so it jumps into that first condition and don't need to jump to the else. And that's why our code will be executed faster. So this is another compiled. So this will be compiled to the assembly instructions by JIT with that actual code. And very important, another aspect is method inlining. So let's say that we have some calc line method. It takes some arguments, it creates some line, and let's say that we have in fourth line we have int y equals l dot get y of x. And every time that method is executed, it needs to jump into line instance and execute get y method. And this is not effective because sometimes it could be even polymorphism involved on chain of invocations. But the JVM and JIT is very smart about it, and if a method is below some thresholds of lines, let's say that it has less than 5 lines of code, it will inline it and this becomes this. So right now in fourth line int y is that operation that was here in the getY method. So it was inlined. And thanks to that, our code doesn't need to jump back and forth, but we have that executed in that place. So that method could be inlined in multiple places in our code. And this is a very important thing to note, that this is good practice to write methods that are not long. So if method will be lower than that line threshold, it will be inlined and our code will be executed faster. So in Java, all getters, setters and everything is almost always inlined.